Right, in this QED TV episode, we're going to look at harmonic motion, specifically the equation for a pendulum. And a pendulum is basically just just a string. Could be a string with like a little ball on the end of it, and this thing will be swinging back and forth like this, and so on. And if we measure from one point all the way over to the other and then back, we call that the period of the pendulum, and that is measured in seconds. And the only thing that really matters about the period of the pendulum is how long it is. What's the length? And then, of course, another thing that depends on is what the gravity constant is. What planet are you doing this on, or what does the gravity? What's the gravity simulated as? And so the equation that we use for the period of a pendulum is given by T. T is the time, the period for one event, one swing over and back. T equals 2 pi times the square root of L over G. So L is the length of the pendulum, and G is the gravitational constant that we are dealing with there. So this is the equation that we're going to use for whenever we're talking about a pendulum, and we can just solve for various things in the equation. And so we'll do a couple problems here. The first problem that we're going to look at is if you have a 1.4 meter long pendulum, so we have length equals 1.4 meters, and the period, the time it takes for one swing over and one swing back, from like here over to here and then back again, is 2.4 seconds. Let's say I'm doing this on some planet, and this is the length of the pendulum. The period is 2.4 seconds. I want to figure out what is gravity. What is gravity on the planet? So I'm going to use my pendulum equation here, and I like to rearrange this to solve for the constant I want to get, and that's going to be gravity. So I'm going to square both sides here, and I'll get period squared equals 2 squared is 4, and then I'd have pi squared, and then I could get rid of the radical, so I'd have L over G. So if I solve for gravity, I'm going to get 4 pi squared L over G, which would be 4 pi squared times the length of the pendulum, which is 1.4 meters, and I can divide that by gravity, which is I got this messed up. This should be t squared right here. T squared. I put the gravity up here, and the t squared should be down below. So this right here is t squared. So that should be instead of writing t squared, I'm messing this up, aren't I? Instead of this, I'm going to put 2.4 squared. So I have 4 pi squared times 1.4 over 2.4 squared, and if you put that in your calculator, it gives you a gravity of about 9.60 meters per second squared, which means we're probably still on the Earth, but since gravity is a little bit lighter, we're probably a little further away, so we might be somewhere on a mountain or something like that. And so that's how you can solve this this pendulum equation for gravity. Let's look at another one here, and I'll try to do a little better job. Let's say that we have a length of a pendulum is 1 meter or 1.0 meters, and I want to know what the period of the pendulum would be. So this looks easy because we're just going to be able to use this equation. But the trick is, I want to know what the period of this 1 meter long pendulum would be if you were at a location of 5,000 kilometers altitude above the Earth, 5,000 kilometers altitude above the Earth. So I can use this equation and sub everything in. It's pretty easy, except for clearly I have a different gravity out there. So to figure out my gravity at that new location, you can remember, I hope, that we use G1 D1 squared equals G2 D2 squared. And the gravity that we're always comparing it to is on the surface of the planet. If we have the planet here and we know our gravity here, we're trying to figure out what's our gravity like out here. So the gravity here is 9.81, and the radius, the distance out to that position right there is the radius of the Earth squared, which is 6,370 kilometers. We can keep it in kilometers here because those are going to cancel out anyway, and we can still get our gravity in meters per second. And we're going to divide that by another d squared, which is the distance all the way from here out to here. So we're going to take our 6,370, we're going to add 5,000 onto it. So I'm going to have 11,370, and never forget to square the distance. And if I figure that out, I'm going to get a gravity of basically about 3.1 meters per second squared if you figure that out. So now all I have to do is just plug it into the period equation. So T is going to equal 2 pi times the square root of L, which was 1 meter, over 3.1. And that, if you plug all that in, that gives you a period of about 3.6 seconds or so. So that's how we can use that equation to figure out the period of a pendulum. Maybe at some place where gravity, we have to figure out gravity before we can do it. Okay, let's do one more thing with this pendulum equation, because we can actually use this pendulum equation for something else. If we have a, if we have the Earth, the nice blue Earth here, and we have a satellite that's going around this Earth. It's coming around here and it's going around the Earth. We have an equation for what the critical velocity is for it to stay in orbit. Hopefully you can remember that critical velocity equation is V equals the square root of GR. What I want to do is I want to start with this velocity, and I want to derive an equation for how long it takes a satellite to go around this particular planet. So how much time to go from here all the way around back to the same spot. That would be the period of the orbit, or the time of the orbit. So velocity, we know, is distance over time. V equals distance over time. And the distance we're traveling is a big circle. So the circle would be, sorry about that. It's V equals a square root of GR. You guys were all probably yelling at me. V equals a square root of GR to go around the critical velocity. So what I was wanting to do there is square both sides. So V squared equals GR. And we know that a velocity is around this is going to be distance divided by time. The distance, of course, around a circle is 2 pi times the radius of the orbit, and that would all be over t. So if I plug this in for my v, I'm going to get, and I square everything, I'm going to get 2 squared would be 4, pi squared would be pi squared, r squared would be r squared, all over the period squared would be t squared, and that would equal g times the radius of the orbit. And if I put t squared on its own side by itself, I'll get t squared. And I'll take the 4 pi, it'll be 4 pi squared, r squared, over gr. And you'll see that an r will cancel out. And so I will get 4 pi squared r over g. And if I then square root both sides, I'm going to get t equals, and if I take the square root of 4, I'm going to get 2, and I take the square root of pi squared, I'm going to get pi. So I'm going to get t equals 2 pi times the square root of r, which would be the distance from here to here, r. We could call that length. It's also a distance, r or L, over the gravity at this place as it's going around here over g. And you'll notice that we get the same equation for this harmonic motion equation up here for a pendulum. The equation for the period of a pendulum is actually the same equation for the period of a satellite to orbit a planet. But when we're orbiting a planet, we need to remember that the L part of our equation, which was the length of a pendulum, is actually the radius of the orbit. This L is the radius of the orbit, and this G would be the gravity of the satellite out there at a particular location. So hopefully we showed that the pendulum equation in the period of an orbit is exactly the same equation. So hopefully that helps you a lot with the pendulum equation.